Hi friends, welcome to follow up. Let's have a look at a newly appeared problem. Problem 2791. Count paths that can form a palindrome in a tree. In this video, we are going to explain a solution based on the use of bitmast and the traditional depth-first search solution. So here we are given a tree. Notice that tree is a special graph. It's a singly connected graph, and if there are n nodes, there will be n-1 edges. So in other words, for any two nodes in the tree, so there is a unique path. This actually is an important observation for this problem. So here we are given a tree rooted at node 0, consisting of n nodes numbered from 0 to n-1. And the tree is represented by a zero-index array called parents of size n. So where parent I is the parent of node I. So since node 0 is the root, so we set that its root is -1. Just regarded this as a flag or mark. So we are also given a string s of length n, where si is the character assigned to the edge between I and parent I. So in other words, there is an edge between parent I, and this edge is marked by the character si, right? So s0 can be ignored. So this is similar as in the parent list, right? So we are required to return the number of pairs of nodes uv such that u is less than v, as the characters assigned to the edges on the path from u to v can be rearranged to form a palindrome. So here, the last paragraph explains what's a palindrome. So basically, it reads the same backwards and forwards. So here are two examples. And the second example is actually very special because all the letters are A. So any two nodes, the corresponding path is a palindrome path. So here you can choose 2 out of 5, right? That's 10. So for the first example, it roughly represents the generic case. So here the output is 8. So you can look at the explanation. However, this explanation explains the output by listing. We need to use some technique to effectively do the counting, right? So next, additional assumptions or constraints. First, the parent list and the s string have the same length, and this length can be as large as 10 to the power 5. So notice that 10 to the power 5 is a decent large number. And also we know that parent I is in between 0 and n-1. And parent 0 is -1, and parent represents a valid tree, and s consists of only lowercase English letters. So this is an important assumption, because there are in total 26 lowercase English letters. So with that said, basically we can explain the overall thought. So this problem is marked as hard. The overall strategy needs some time to digest. So here the strategy is the use of bitmast and the depth-first based traversal. So here we want to explain several observations and how we use bitmast and how to do the counting. So the observation 1 is the following: the path between two nodes uv. So here this path will be unique, right? So it can be rearranged to form a palindrome. So if and only if at most one character in the path string appears odd number of times. So in particular, the character order is not important or is irrelevant for this problem. For example, you have CA and AC, they're the same, right? So this is the path from 0 to 3. So this is the first observation. The second observation is that how we count the parities of the letters in the path. Let's consider the path between U and V. So we are going to call LCA, the least common ancestor of the two nodes UV, as LCA. For example, you have 3 and 4, so the LCA will be 1. But for 3 and 2, the LCA will be the root 0, right? So this is a very classic concept. So assume that we have this LCA. Then the path between U and V, it can be computed like this. the LC from U, and then the LC from V. So this equality is a strict equality. And then it also equals, because you can think of the path from between 3 and 4, right? Then we can also compute the path from 0 to 3, that is root from U, and 0 to 4, that is root from V. So then the root from U minus the root from the LC, that is from 0 to 1. So this will be the path corresponding to LCA to U. Similarly, these two items corresponding to the path from LCA to V. So this equality is a strict equality. And then, so we do this rearrangement. So we have path from root to U and path from root to V, and then minus twice of these things. So because we minus twice, and each letter in this path actually counts 2 times, therefore they do not affect the parities, right? If a letter in this path appears overall even number of times, you minus 2 times the occurrences, it will still appear even number of times, similarly for odd number of times. So to compute letters parities, here by parity we mean even or odd. So we just need to consider this, right? Path UV equals path from root to U and path from root to V. So we do this in the sense of modulo a multiple of this path, right? So we can write directly as equality, right? So this equality is not a strict equality. It means we do not change the letters parities. So for example, in example 1, we have path 3 and 4. So it's represented by AB, right? So then we can use this formula, right? So this is the from root to 3. This is from root to 4. And their common ancestor is 1. So from root to 1 is corresponding to a letter C. So we get minus 2. So we're going to get AB, right? So or you can see it's just the CCAB, but C appears even number of times. It does not affect if it's a valid path. By valid, we mean we can rearrange that to make it a palindrome path. So here, as I marked, this equality means letters parity do not change. So this is the 2 observations that are important for us and in this specific problem. So next, we want to get a compact representation on how to represent the path and record the letters frequencies or even and oddness. So for this, actually, we can use bit representation. So for each character, we mark it to a bit position. Then basically the number corresponding to that position is 2 to the power of that position. So here I'm going to use this representation. So for example, A is the first letter, so it's going to correspond to the first bit position, corresponding to this bit operation, and corresponding to 2 to the power of 0. So in binary, it's just a 1, or in decimal, it's just a 1 also. And then for B, so it's corresponding to the second bit position, then it's 2 to the power 1, right? That's 1, 0 in binary, and in decimal is 2. So similarly, Z corresponding to this one, right? 25th. So it's 2 to the power 25th. And then if you write in binary, it will be 1 followed by 25 zeros. So in other words, connecting to this problem, we use this in binary representation, for example, 5. So it's 0, 1, 1, 0, 1. So this is in binary. It means C appears odd number of times, and A appears odd number of times. For example, this path from 0 to 3 is corresponding to CA, right? CA and AC are the same, right? So this both corresponding to 0 or 1, 0, 1. So this is the example. So path 3. So this is the 1, 0, 1, corresponding to 5, and the path 0 to 4. This is CB, right? So CB is a 1, 1, 0. So it's corresponding to 6 in decimal, right? So to consider the letters parities for path 3 to 4, right? We do the following, right? We just count this one, and then do this exclusive OR with this one. So here we have 1, 0, 1, right, for 5, and 1, 1, 0 for 6. So here in the third bit position, 2 ones, so result 0. In the second one, they have 0 and 1, we result 1. In the last one, we have 1 and 0, result 1. So this means in the pass 3, the letter A appears odd number times, and letter B appears odd number times, right? So because there are two letters appearing odd number times, so this pass cannot rearrange to be a palindrome. So this is basically the ingredients we are going to use for the bit mask representation in this problem to record the or to check the parities of letters in a pass. So next, I want to explain the big picture on depth-first search in this problem. So our goal is to use depth-first search to compute the letter parities of this path from root to the node. So here we are going to use a mask value, so in other words, a decimal number or binary number to represent that. And then we're going to use a counter or dictionary to count valid paths and storing the path mask value and their frequencies. Basically, tell me if the path have such a mask value, how many times such a path have appeared. So here, the first item is easy to understand, right? Because depth-first search or breadth-first search is typical graph traversal algorithm. And for the second item, so basically assume that we have a node U. It has mask value current. In other words, path from root to U. This is the mask value. So here equal, it means in the sense of counting parities. Then to check with which node V path UV is valid. In other words, can be rearranged to be a palindrome path. So it reduces to check with which nodes V. We assume that the mask value from the root to this node V is X. We have the following. First case is current exclusive OR with this X is 0. In other words, this means no letters in the path UV appear odd number times. Another class of cases is that the current exclusive is this X equals 1. So in other words, there's only one letter appears odd number times. So here I runs from 0 to 25, or with the letters involved in the example. Or so for example, here it involves A, B, C, 3, right? 3 letters. We just use 3 bit positions. So here it appears just 1, so we just need to use 1 bit positions. So in the second case, it corresponds to that there's only the ith letter appears odd number times, right? So in case 1, if we do exclusive OR in both sides with current, so we get something like this, right? And then current exclusive OR with itself yields 0. So the left-hand side will be X. So X will be current. We do the same thing for the second class. So current exclusive OR with current will be 0. 0 exclusive OR with X will be X. So X will be this number. Then basically we just need to check the passes with the mask value equals current or current exclusive OR with a bit position, right? So this is our second item. So here I want to leave a challenge. So basically, after we explain the code, it's nice actually to do a walkthrough using the example 1 with the solution we will explain. So this will help one to really digest the code. So with that said, let's look at the coding part. So basically, we want to encode the above explanations into code format. First, I'm going to build the tree. So we regard this one as part 1 or step 1. So this basically we build a graph, right? So the graph, the tree is a special graph. In other words, singly connected, and there are n-1 edges if there are n nodes, right? So a property is that between any two nodes, there is only one path. There's a unique path, right? So let's do this. Let's call it tree. We can use adjacency list, right? So basically for I, so let's see, for I use dummy index for in range length of the parent length, right? Notice that the length of parent and the length of string are the same, right? And so we can actually introduce a variable. Let's call it let's call it n. Right? It's much clean. So then for range n, right? So the index will corresponding to an empty list. So we are going to set its neighbors, right, or the offsprings. Now let's iterate, right, for I in range 1 to n, because the first letter in parent corresponds to the root, right? It has no parents. So then basically what we want to do is we set tree. The parent is nothing but parent I. So equals, because it's empty list, we're going to append I. So this way we finished building the tree. Next we're going to build the mask. Build the mask representation for each letter. So here we can do this. So mask. So for each letter in the string S, so basically we want to assign it as a number. This number is one shifted to the left by this number, by the ordinality of this character minus ordinality of letter A. So in other words, it's a relative position. For example, A will correspond to 0th position, and B corresponding to the first position, as explained above. So basically, for character in S. So each letter will correspond to a number. So for example, A can be appear many times. So there are some equal elements. But in this way of writing, for the index, we're going to correspond to that letter, and the value, mask value, will be the value corresponding to that single character. So this is the bit mask. Next, we are going to do BFS. So for this, we also want to initialize a count variable as an answer or result. So we are going to return its final state. Notice that this one, the integer, is immutable. We're going to use a non-local keyword later. So also we want to use a counter, right? So the counter is let's use collections and default dictionary. So it's int. So for this, originally, so we want to have something like if empty string, right, at the root. If you consider the root from the root of itself, we can regard it empty. So you can think the empty has a representation 0, so appears west, right? So you can think of this 0 corresponding to this one, empty string, right? So this is the one way to digest, right? And then what we want to do, so the DFS. So we're going to accept a node and the current mask value, right? So now what we want to do, first we want to, in between the traversal, we are going to update the counting. So let's first make this variable non-local so that we can continuously update the value of the answer, in other words, the counting. So that's the first step. And then what we want to do, we want to traverse each edge. In other words, we want to check the neighbors or the children of this node. So basically, for children in tree, right? So the current node. Then we want to update the mask value. So update the mask value. So the current mask value is current equals the current mask, the value up to I. Then plus the value corresponding to this edge is nothing but masks. So here we do a lookup. So for child, right? And then basically we want to check if there are some paths can have like satisfy the conditions here. So we can do the counting, right? If there are some paths already have mask value equals current or equals current, like shifted, exclusive or with a shifted representation. In other words, powers of 2. So for this, let's first check this. Answer, first we increment by this one. So in our counter, so we want to check if the x equals the current, right? That is the current So this is very easy to understand. So this is the corresponding to case 1. And then for the second case, so we are going to do this for I in range. So here we use 26 bit position. In other words, check A and Z. Though some letters may not appear in the string S, so we regard it appear even number of times. So this way we are going to increment the answer by we check the contents or frequencies, that is current exclusive all with 1 shifted to the left by this by I position, right? And then after we do this case 1 and case 2, what we want to do, we want to put the current value into the hash map. So current is incremented by 1. So if current is not inside the count or dictionary, due to the way we set its content to be 0, we just need to increment by 1. We don't need to do a get and check if the k is inside. If we use a vanilla dictionary, right? Like initialize like this or this here. So let me make a remark. Store or update the frequency of current. This is the mask value, right? And then what we are going to do, we do the traversal for this child, right, with current. So this is our major part of the work. So next, basically, we prepare the return. So this is actually simple. We call this DFS function. So originally it corresponds to empty string, right? It's corresponding to 0. This is the root, and then the value is also 0. So notice that the first 0 is the root node. The second 0 is, you can understand it as an empty string, or you can understand as a 0, right? And then what we want to do, because if we call this function, so this will be automatically updated. So what we want to do is to return the final state of this answer. So this actually forms a full solution format to this problem. So before we make any comments, let's do a test. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes the generic case. So here we can actually study and change a little bit about the coding. So here let me copy this full thing here, and then I'm going to mark this one as version v1. So here what I want to do in this version, I just want to use the positions of the letters appeared. In other words, I don't need to consider 26, right? For this, basically we can do something like here, right? So we want to see the largest bit position. So max bit position. So originally let's set it to be 0, just one letter. So basically we for character in S, right? So max bit position, I'm going to update it max bit position. So to this one, ordinality of character minus ordinality of this A, right? So we recorded this this one, and then we just need to examine this number of bit positions here, and then but we can change here to be max bit position +1, right? Because +1 will, the largest index will be here, right? And then we do this. So this actually, I don't know if it does not improve the time complexity, but we don't need to iterate all the letters. For example, like in this case, we just need to use once. But here is a for loop, but here is another for loop. Essentially, it does not improve time, but it actually will deepen our understanding. So now let's test this version. Yeah, it passes the first example. Now let's look at the generic case. yeah, it passes all the generic cases. So with that said, basically that's about it for this video. So here we provided one way of doing the coding. So it's encouraged to do a walkthrough using example 1. So you can monitor the change of this the answers variable and the change of this count, and also the representations of this passes. And if you have difficulty in understanding or digest the coding here, so you can come back here, like these two observations and base mask representations. So with that said, I guess that's about it for this video. Thank you.